So my name is Wilson, and today I'll talk about my what I did for my master's thesis, adaptive learning from demonstration for industrial robots. So before I start, I would like to mention that there was actually a lot of things that I had to omit because probably I don't have enough time to cover everything, especially technical details, but please feel free to ask me anything after the presentation. Why is it not? Right. So first, an overview. I would first like to talk about the motivation of this topic. So why learning from demonstration, and how is it important for industry or manufacturing in particular. In order to understand that, I'll have to go a bit into the background of manufacturing and what kind of role learning from demonstration can play in this. Then I would like to talk about some industrial criteria for which these algorithms need to conform to in order to be useful in industry. So just like everything that we make for industry, they need to conform to certain criteria before they are actually applicable. These criteria were then used to design and implement LAB, which stands for Learning, Adaptation, Production. And today I would also like to share some of the experiments I did and the results of LAB, and I will conclude this presentation by talking about some future work. So first, why learning from demonstration? Well, as you may know, robots are typically used in these specially built environments which are very controlled, and building these environments and instructing these robots takes a lot of time. Learning from demonstration can save a lot of time, cost, and effort because usually it's much faster and easier to demonstrate a certain task because it's more intuitive for non-experts. We would usually need to hire experts to program the robot for them. And even for those experts, programming a robot such that it can work autonomously in any kind of situation is very hard. Not only that, but there will also be a less need for specially designed environments because we could simply teach a robot to deal with any environment. So I do believe that we should actually make the robot adapt to the environment instead of the other way around, adapt the environment for the robot, which is what we're doing now. So on the other hand, a shift has also been observed in industry where people shift from mass production to mass customization. So nowadays, instead of wanting to produce a lot of the same items, we are shifting to the type of manufacturing where we produce smaller batches, or still large but relatively small compared to mass manufacturing, where each batch is basically one type of item, and the other batch is basically the same item but maybe coming in a different color or different shape or with different accessories. So slightly different but more or less the same. This gave rise to a number of small and medium enterprises which employed a high-mix, low-volume manufacturing paradigm. And I will explain in a minute what high-mix, low-volume means exactly, but the conclusion is that we need more robots that are able to cope with more variety in production. So we need more dynamic and reconfigurable robots for which learning from demonstration is more beneficial than traditional programming, where we would need to reprogram the whole thing over again for the smallest changes. So what is this high mix, low volume exactly? Well, manufacturing paradigms can usually be categorized by mix and volume, where mix refers to variety and volume refers to quantity. So typically we are at the bottom right corner here in the low mix, high volume segment, which is the typical mass manufacturing scenario. So again, a lot of the same things, so variety is low and volume is high. For which, like I mentioned, we use traditional programming now. On the other end of the volume spectrum, we have manual labor in low mix, low volume. So think about luxury items such as luxury bags or designer clothes or watches. So these are usually very exclusive items and not that many people buy them. So they're also produced at very low quantities. So usually it's not even worth considering automation for this segment. What we're interested in is, however, the high mix, low volume segment, because this segment is characterized by a high variety of tasks and rapid production cycles. So whenever one batch is finished, we need to change the task slightly to cope for the next batch. So in this case, the robot needs to be reprogrammed frequently, for which, again, learning from demonstration is simply more efficient and effective. So industrial criteria. Assuming that this trend will go on and that learning from demonstration will become more and more important, we need to consider about what makes these kind of algorithms actually useful in industry. So a lot of work has already been done on learning from demonstration, but not all of them are readily applicable in industry. So I thought about what are the requirements for these algorithms to conform to, and most of these are actually pretty straightforward. So of course, the robot and the learning algorithm should be precise, accurate, fast, but also highly generalizable. So the robot should be able to adapt to different environments or changes in the task. It should be able to learn different tasks, but without changing the system, and should also be easily transferable to other platforms. Not only that, but learning fatigue is also a very important thing. So you don't want to spend a lot of time to teach a robot a certain task. It should be very easy. And lastly, this would usually mean that you want low system complexity, because the simpler the system is to use, the easier it's to understand for non-experts. So learning fatigue will usually be lower in that case, and generalizability will also be higher because there will be less dependency. So it should, in theory, be easier to transfer the system from one platform to the other. So although all of these are very straightforward, actually, at least back when I was working on this, not that many work out there actually focus on all of these aspects. So they would usually only focus on one or two, and generalizability, for example, is a very popular topic. But I do believe that it's very important to address all of them if we want to use this in practical situations. So I took all these criteria and decided to design and implement my own algorithm, which is called Learning, Adaptation, Production, or LAP in short. So as you can see, it consists of 3 phases, namely the learning phase, adaptation phase, and production phase. So in the first phase, I just used existing ordinary learning from demonstration algorithms to learn an initial task. And if the user is happy with this task, he can immediately go to phase 3 and use it for production. But you could also imagine that maybe during teaching the task, maybe there are some small mistakes or just these small segments that you want to correct. So in this case, I introduced the adaptation phase, where the user can iteratively adapt certain specified segments of the initially learned task to focus on correcting only the mistakes instead of reteaching the whole task over again. This is not only useful for correcting mistakes, but you could also imagine that maybe after a while the task changes slightly. So in general the task is more or less the same, but maybe instead of wanting to pick the item here, we want to pick it up and place it here and place it somewhere else again. So more or less the same task, slightly different. So for that purpose, the adaptation phase could also be useful because the task is more or less the same, but you only want to change small parts of it. So in the next few slides, I will discuss each of these phases in more detail. So beginning with the learning phase, in order to record the demonstrations, I use Kinesthetic Teaching, and well, probably you've never heard of it before, but so basically, there are many different ways of recording demonstrations, right? You could use external cameras, for example, that can track the human body. And for example, if I do something, then the camera could track what I'm doing and transfer those demonstrations to the robot. Or I could also put some sensors on my body that track my body movements. Kinesthetic teaching, however, is the type of teaching where you basically take the robot by the hands and guide it. So you just like how we teach children how to do something, you just grasp it by the hand and show how it's done. And this is the most direct and very intuitive way of teaching. So I chose for kinesthetic teaching in an attempt to decrease learning fatigue. And also system complexity will be reduced because for kinesthetic teaching you only need the encoders that are already on board of the robot. So you don't need any additional subsystems, such as you don't need a camera, or you don't need complex algorithms that track the human body. You only need the robot, and that's it. So once these user demonstrations are recorded, we need to use a learning algorithm to learn these demonstrations, for which I use dynamical movement primitives to learn Cartesian positions. So I chose for Cartesian space because most manipulation tasks can be defined in Cartesian space, which means that if we learn a time series of Cartesian positions, then we can learn a wide range of different tasks that can be encoded in Cartesian space. Which means that the learned task is easily transferable to robots, assuming that they have at least the same number of degrees of freedom, and assuming that we actually have the inverse kinematics solver. And this was all in an attempt to improve the generalizability. So a bit more detail about dynamical movement primitives. So these are basically a set of dynamical systems that encode any kind of trajectory. So these can be joint positions or joint forces, but in my case they will be Cartesian positions. And they have powerful features such as independence of time, guaranteed goal convergence, disturbance rejection, etc. So equation 1 is basically the core of the DMP. So this part here is basically it's actually a very simple PD controller which drives the system from its current state Y to its goal state G. So it simply brings the system from start to end. But for a robot, it's not only important to end up at the goal position, you might want to be able to track a very specific trajectory. So in this case, we have a nonlinear forcing term F, which is used to shape the trajectory to have any kind of shape you want. And this f of x is actually a function of weighted Gaussian functions, as depicted here by equation 2. And so the forcing terms will basically look like this. So we have Gaussian functions over here, we have the weights. The weights are multiplied by the Gaussians, they're all summed up, and this will be an example of a trajectory that we might want to follow. And note that these weights can simply be learned by any function approximator, such as Gaussian processes or Gaussian mixture models. But in my case, I chose to use locally weighted regression, which is a one-shot learning algorithm. So we only need one demonstration for the robot to learn this trajectory. Again, I chose a one-shot learning algorithm to decrease learning fatigue. You don't want to show a lot of demonstrations. And note that the trajectory can be easily adjusted simply by adjusting the weights of interest. So let's say that we are interested in adapting only this part. We'll only need to relearn these two weights and keep the rest the same. And that should increase adaptability because it's very easy to adjust the trajectory in this way. So next is the adaptation phase. I didn't mention before, but I'm using a human in a loop adaptation approach here. So what do I mean? So usually in feedback systems, we need sensors and complex algorithms that track the state of the system and use that as a feedback to reduce the error. Sometimes implementing these algorithms and selecting the right sensors is a very hard task. Well, we as humans, we are actually the best judge to judge task performance for a robot. So for example, if I teach a robot to grasp something like this and it goes all the way there, then it's obviously wrong, right? But for the robot, it's not that obvious. But for us, it is. So why don't we act as the sensor and be the high-level correction and evaluation mechanism? Because humans are much better and more efficient at judging task performance than all these complex algorithms and sensors. And this will decrease system complexity drastically, because if a robot does something wrong, we just simply push it in the right direction or reteach the parts that need more attention. And this can be done more in an iteratively fashion until satisfactory performance is obtained. So we can kind of like keep correcting the robot until we have the accuracy that's desired. And again, for DMP, this simply means readjusting and relearning the weights of interest. So if these are correct, we just leave them. And if these are wrong, we just reteach only that part. So finally, the robot can move to production phase, where we remove the robot, the human from the loop, and the robot will just transit to high-speed position mode. And performance of this phase is actually platform dependent, unfortunately. That kind of depends on how fast and accurate your robot actually is. So during my thesis, I actually didn't have enough time to focus on this phase, so I will kind of skip it for today. So the experiments I ran were done on this robot, which is the KUKA LBR EVA. This cobot that has a low stiffness control mode, which is again also needed to do the kinesthetic teaching, because if you want to be able to drag the robot around, you can't do that if the robot's very stiff. So we need to be able to control the stiffness. And the experiment I did was drawing large 8 figures in the learning phase. So I drew basically an 8-figure in the learning phase, and then in the adaptation phase I decided that I want to make it smaller. So I want to keep the head of the 8 big and readjust the smaller, the lower part of the 8 to become smaller. So in the adaptation phase, I make the robot switch to low stiffness mode when the user wants to adapt. And then the user can reteach the segment of interest to make a smaller 8. And the original trajectory will then be executed again when we're done with adaptation. And finally, the adapted trajectory will be executed in position control mode in the production phase. So I still have some time, I guess. Just a quick video of how this looks like, oh, or not. So I'll just skip all the text. So here you see me teaching the initial task. So this is the 8-figure that I initially learned. And then I want to specify the lower part to become not like this, but to become smaller. Okay, so internet. So the internet connection is also not that good. But, so yeah, so I adapt the lower part of the 8-figure to become smaller. I think you get the idea. And in the end, we are indeed able to draw the lower part, redraw the lower part of the 8 while keeping the rest the same. Right. So this is the result. So again, the first initial demonstration, the first learned task, and then the adaptation where we have a smaller 8-figure while keeping this as much as the same as possible. To show that this task is also applicable for other kind of tasks and not only for drawing 8 figures, I also did a pick and place demo, which I probably don't have enough time to show. But anyway, the idea is that using the same learning algorithm, I was able to learn different kind of tasks. So future work. It was maybe not so obvious, but there are still some inaccuracies. So this was due to the connections between the adapted segment and the original trajectory. So I needed to improve the connections between the adapted segment and the original trajectory. And also note that I mentioned that I only learned the Cartesian positions and not the full Cartesian pose, because in order to make DMPs track rotations, we need to use a very special trick, which was actually published in another paper. But for this idea, I used the original DMPs first, which are not able to learn orientations. But it should be easily interchangeable. What I was interested in was to choose different function approximators to play around with the trade-offs of the industrial criteria. So this time I went for low learning fatigue, but then you basically sacrifice generalizability, right? So if you are able to show more demonstrations, the robot might be able to generalize over all these different demonstrations, but then you also sacrifice learning fatigue. So this is something that we need to play around with. And like I said, I didn't have enough time to focus on the production phase, so if I were to continue with this work, I would probably also focus on that. My ex-colleagues, however, already addressed the first point, and they published a new paper, DMP+, where they improved accuracy drastically by simply adding a bias term to learn instead of only using weighted functions, so we have a bias term. And they use truncated kernels instead of full Gaussian kernels, which could have transient Fortune terms because they go to infinite. But anyway, using truncated kernels, it should be easier to select those kernels that matter. But anyway, I did not work on this work, so I don't know too much about it, so please check it out here. So I think it's time. So thank you for your attention, and I hope that you enjoyed the presentation. So are there any questions?
So the ideal is to have the machine, like you direct the machine learns. If I understand correctly, what you still have a lot of interaction with the code, where you basically then tell it which functions to redo or to address.
No, actually, so that's actually done automatically. So it was not maybe it was not really obvious because I skipped through the video. But actually, I first teach the initial 8, and then the robot will start executing it in very low speed, and then I actually say stop. So the robot will stop there and switch to impedance mode, and then I have some time to show like what the new adaptation should be, and the algorithm actually tracks which part of the initial task this actually is, and will try to match like, okay, the newly shown demonstration and the previous learned task, so which part needs to be replaced, and that's actually done automatically. So yeah.
Oh, okay, cool. So it makes a guess then at which point it's now onto the old program, and then it should match to the old...
Not just guessing, but actually we just say start and stop, like start adaptation phase and stop adaptation phase, because again, for us it's very obvious which part of the segment we want to change, so we just tell the robot. And actually I used a technique called dynamic time warping that basically matches key points of two time series data that looks for similarities. So the parts that are the same are, well, the same. And the part that are not is probably the adaptation part. So this is a technique that I use to find the similarities.
I see.
Yeah. Right. Next question? No? Then thank you for your attention.